Okay. Today we're going to start with polarity and polar bonds, and we're going to talk about negativity and distribution of charges in a polar molecule. We're going to briefly talk about what happens to polar molecules when we place those molecules in between charged plates, a positive and a negative plate. And I think the toughest thing of today will be talking about intermolecular attractions compared with ionic bonds, comparing ionic bonds and three different types of intermolecular attractions for covalent bonds. And we'll briefly talk about network solids, but we don't do a lot on those. Okay, so covalent bonding is it consists of sharing of electrons. We all know that. And the question is, we're talking about polarity, is if the pole is equal. We're going to start our conversations today talking about diatomic molecules, two atom molecules. And the first ones we're going to talk about are equal sharing, and those would be our Brinkelhoffs.
Anything on your computer?
Is that me?
I read pretty much all day.
Sorry. Okay. That was me. So if I have any of my Brinkelhoffs, BR, if I have two bromines, and they're chemically combined with a covalent bond, which has the greater attraction, this bromine or this bromine? They're equal. In that tug of war, since the electronegativity is the same for each bromine, then their attraction for that shared pair is equal. And we end up with a non-polar covalent bond. So if I ever have a Brinkelhoff, which is a diatomic molecule that's Br, I, N, Cl, H, O, or F, those diatomics, they will always be nonpolar because there are two atoms of the same element combined. If we have different atoms, there's going to be an unequal sharing. What's the most electronegative element on the periodic table? Fluorine. So something bonded with fluorine, other than fluorine, for instance, a hydrogen, will form a polar bond because the electrons are not shared equally. There's unequal sharing. The higher electronegative element, the element that has the higher electronegativity, pulls that shared pair closer, and it creates an area of electron deficiency and an area of an electron surplus that gives us a partial positive and negative charge. And we call that a polar bond. Cute little Dr. Cotton slide. Thank you, Dr. Cotton. Okay, here's a list of electronegativities. You don't have to memorize this, and I'll have one of these for you either today or block day. I haven't decided. But these elements right here are going to be first and foremost in our minds today. Fluorine is by far the most electronegative element at 4.0. Second, by far, is oxygen with 3.5. Do you agree with that? And then I've got a 3.0 and a 3.0 in these four elements right here. So those four elements are by far the four most electronegative elements on the periodic table. And if we look at trends, since this is highest, what happens as we go down? It decreases and it increases that way. So let's consider HCl. H has an electronegativity of 2.1. Chlorine has an electronegativity of 3.0. So if I have an H and a Cl share, they are going to not share equally. Do you agree with that? And this will be on our next slides as well, but I'm going to put this up here too. H, I'm going to make a bond like this, and Cl. Now, which of those two elements, based on those two electronegativities, is going to pull this shared pair of electrons closer? chlorine. It's got a much larger attraction. Much larger attraction. And we'll learn about this in one of the next slides. That's going to give this a partially negative charge. That's a lowercase d, and we'll see that again on the next slide. And it's going to leave this electron deficient, so that's going to have a partially positive charge. So chlorine is going to acquire a slightly negative charge, and hydrogen is going to acquire a slightly positive charge. On this pink sheet that you picked up today, on the back side, there's a table down here. And if you find the electronegativity difference, what's the electronegativity difference? What's the difference in these two numbers? 0.9. Look up on that table. How would we classify this? This is moderately polar covalent. You don't have to memorize those, but we'll take a look at these in greater detail when we're working on our lab. I want to draw your attention to where it says ionic. Anything with an electronegativity difference over 1.85, we're going to classify as ionic. And if I go back to this slide right here, take a look at sodium. Sodium is 0.9 and chlorine is 2.0. The difference is 2.1, do you agree? A metal and a non-metal, a group 1A and a group 7A. That's a difference of 2.1, which is well above 1.85. Do you agree? I've seen tables where the difference that's required for ionic is as high as 2, and I've seen it where the difference is as low as like 1.7. So there's not like a set number that's ionic in character. Is that clear to everybody? So as you move on in your world of science, you might see different tables where they have a different scheme of classification. Just use whatever you're given. Okay, so this is what we were talking about earlier. This shared pair of electrons is different than ionic bonds. In ionic, the metal gives its electron, for all practical purposes, donates an entire negative charge from the metal to the nonmetal. If it donates 2 electrons, it donates 2 negative charges. This is a partial charge. And the more polar a substance is, the greater the negative character and the greater the positive character. I've seen it done like this, but not much anymore. We always use delta plus and delta minus. And you'll do this when you're doing your lab. So that would be a polar bond. H and Cl are 2 different elements with 2 different electronegativities. Therefore, the H and Cl bond is polar. Do you agree with that? Polar bonds tend to, or have the ability to affect an entire molecule. So if I have a polar bond, it can make a polar molecule. HCl is a polar bond, so the resulting molecule is polar. Any molecule that has 2 poles, like HCl, I don't know if you can see this very well. Since that has a delta minus and that has a delta plus, there are 2 poles, and we call that a dipole. Not too hard there. So dipole is an interesting word, and it's sort of challenging, but all it means is that I have 2 poles, a positive and a negative. Does that make sense? So don't panic when you see that word. Here's another molecule. This is carbon dioxide, and if I was going to have you draw this, I would insist that you put these electrons around here. Do you see what I just did? That's correct. That's one that we've already done, I believe twice. We did it in the front page of our packet, and we did it during our lecture, I think last class. This bond, the CO bond, is a polar bond. And O is negative, and this has a positive character. Do you agree with that statement? O is the second most electronegative, so obviously that's going to be a true statement. This bond is also negative, and this is positive. So do you agree that each of those two bonds is a polar bond? Say yes.
Yes.
Okay, each of these bonds is polar, but this is a non-polar molecule. Please look with me at this side of the sheet. And look at those two columns that say polar molecules and non-polar molecules. Can you find this format listed there in those diagrams? And which one side is it on? It is, and I believe I've represented it as AWA. Do you agree? So this is a triatomic, 3-atom molecule. It's a 3-atom molecule. What's its shape? It says right there, what is it? Linear. And it's on the side that says nonpolar, because each of these oxygens is pulling with the same electronegativity on that central carbon. Do you agree with that statement? Look please on the other side. Do you see on the polar side any other possibilities for triatomic molecules? Do you see any others with 3? I see 3 of them. One's linear, and instead of this, like an O, double bond C, double bond O, what if I had an S, double bond C, double bond O? It's in the same family, but this one would be polar. Because which one of these two, sulfur or oxygen, would acquire an electron, what's the word I'm looking for? Extra. That one, because it's more electronegative, which would mean this one was electron deficient. Does that make sense? And this format is that AWB or AWB, is that right? Format. And then the next one we're not going to see too much, and I'm going to save my other 2 triatomics. But both the other 2 triatomics, how do they differ from the ones we were just looking at? What do they have? What do you see on those next 2 diagrams on the polar side? Do you see anything there that's different? Yep. Unshared pairs of electrons. And you'll recall that we said that those were going to be critical when we got a little further in this chapter. In fact, here's water. We've drawn water like this. And if you look at this shape and you look at the polar side, do you see this shape? What do we officially call this shape? Bent. And here's what it's going to look like when you build it. And you can you see how this fits on there? So my 2 unshared pairs of electrons are up here on my oxygen. Do you agree with that? Now this has a polar bond. This is a polar bond. Not only are they polar bonds, but we have unshared pairs of electrons that are negative in character. Here we don't. And we're going to find out later that water is highly polar. And this bent shape, these 2 unshared pairs of electrons, and the fact that there's 2 hydrogens here, which will be critical in a few minutes that they're hydrogens, contribute to water's extremely polar nature. Water is very, very polar. And that's polar on many levels. If I put this molecule between charged plates, remember, this side of this side of the molecule is negative because it's got the two unshared pairs of electrons, and oxygen is more electronegative. These two parts are positive, delta minus, delta plus. So if I put this in a field with a positive plate up here and a negative plate right here, will it orient like this or like this? O on the top or O on the bottom? Yep, because the positive and negative opposites attract. And if this is positive and positive, what do like charges do? Repel, so it'll turn it over. So that's what we mean when we say that they'll line up, that they'll orient and charged plates. Okay, now we're going to talk about intermolecular charges. And I want to just take a moment and make sure that you switch your thinking. We've been talking about the bonds within this molecule. This bond between these two is polar. This bond is polar. Now we're going to start talking about intermolecular bonds. How does this molecule interact with this molecule? And we're going to talk about 3 different things that can happen in covalent bonding. The first thing we're going to talk about, the weakest of all forces, is called dispersion. And I call these London dispersion forces, or the London dispersion force. And I usually abbreviate these LDF. From anything that I've prepared, this is what it's going to say. So if you see any keys that I've done or any work that I've done, this is what it won't say dispersion, it'll say London dispersion. Is that clear to everybody? They are the weakest of all intermolecular forces. They're caused by electrons moving. And until we get to absolute zero, you know what electrons do? Move. That's part of the deal. The London dispersion forces increases as we get more electrons. If London dispersion forces are due to motion, if I quadruple how many electrons are moving, do I quadruple the motion as well? I do. So the more motion, the more attraction between particles. Everybody's favorite group of elements to look at are these right here. Fluorine is a gas, chlorine is a gas, bromine's a liquid, and iodine is a solid. Yet each one of these, and I'm going to use the letter E for element, because nothing has an E, and the letter E for element, every one of those halogens has the same electron configuration, just like this. Now they're diatomics, but I'm just going to pretend they're not. This one, if it's fluorine or if it's chlorine, they're out floating around in the air, and they don't have a strong enough attraction between them to force formation of a liquid. There's no attraction. They're gases. The lowest forces would be most likely to be what physical state? The lowest attraction between molecules would likely be gases. Because if they attract, guess what? They're going to first turn to liquids, they'll flow, and then they'll turn to solids that just vibrate. So fluorine has 9 electrons, right? And it's a Brinkelhoff, so double that. What's that? 18 electrons. Chlorine has, double it. These are all Brinkelhoffs. It has 34. 18 electrons, not enough to get it out of the gaseous stage. Not enough motion. 34 electrons, not enough motion. But look at this. When I go to 70 electrons, those molecules are held close enough together that they're no longer just flying around like gases, but they get close enough that they flow. They haven't gotten enough attraction yet to solidify, but they can flow. Which has greater attraction between the particles, of liquid or gas? The liquid. So there's greater attraction. Then we go all the way up to from 70 to 106. And what happens when we get to 106? We have enough electron motion that we can form a solid. Does that make sense to you? Each one of those, by adding electrons, we increase the motion. 18 electrons doesn't have nearly as much motion as 106. If I got 106 electrons moving, that's a lot more motion than 18 electrons moving. Do you agree with that? And that motion is enough to do what they call induce a dipole moment. You know, I'm not even going to worry about that today. But it induces a little moment. It makes your London dispersion forces greater. Yes.
If lithium has 3 electrons, why is it a solid and it's not a brick wall? Is that
Because lithium doesn't covalently bond.
oh.
It ionizes. That's a good question. What we're talking about now is covalent bonding, and covalent bonding occurs between or among non-metals only. Everything on this side of the stair step and hydrogen. Okay? So this is one of my favorite essay questions for this unit. Okay, the second or middle level attraction is called dipole interaction. I want to go back to one thing and I want you to jot this down. For London dispersion forces, you only have London dispersion forces in non-polar molecules. If you ever draw an electron structure and determine it's non-polar, what will your intermolecular forces be? London dispersion. Do you agree? Only London dispersion forces. So LDF is nonpolar only. Dipole, and I usually call these still, just from the olden days, dipole, dipole. And yes, I am nerdy enough just to abbreviate those dips. So when I call dipole, dipole, that's what you'll see me write, is when we have a polar molecule. So it's when I have polarity. This one is for polar molecules. And I'm going to bring that even further. I'm not going to spend a lot of time on dipole right now, but if you draw a structural formula like we did on page 1 of that packet, if you draw a structural formula and it's a polar molecule, then your intermolecular attraction has to be dipole. Is that clear? That said, then I'm going to give you a special deal. Dipole interactions are based on the concept that opposites attract. Now, in an ionic compound like this, I have a big transfer. This ends up with a 1 plus, this ends up with a 1 minus, and those are very, very strongly attracted. And the physical state at room temperature of every ionic substance is solid. Every salt is solid. There's no such thing as a naturally occurring at room temperature liquid salt, because that plus minus attraction is just too big to be a liquid. Does that make sense? We'll find out that to heat this up to melting, I think, is like 3,500 degrees. You know, that's hot. That's really hot. So here we've got a hydrogen and a fluorine, and I've got a plus and a minus, and it will be attracted to a plus and a minus. So it goes plus, minus, plus, minus, plus, minus. Plus is attracted to minus. See if you can find the 2 errors. There's 2 errors on this one. Let's race. Where? Right here, there's 2 minuses. Where's the other one? 2 pluses. But I've already told you I never changed Dr. Cotton. I'm not sure I'd change it. I'd have to put a whole nother molecule in there. Do you agree? Okay. And then our third and strongest type of attraction is hydrogen bonding. This is our third and strongest. It's the strongest of intermolecular bonding for covalent compounds. And it's when we have hydrogen bonded with one of these three. It has to be, there has to be bonds like this included. If there aren't bonds like that, then it's not hydrogen bonding. So if you have H with an S, guess what? Not hydrogen bonding. And we'll practice those when we do our lab. It is the strongest of the covalent intermolecular forces. The hydrogen, well, I'll show you that in a moment. So it's the strongest of these. Dispersion forces are the weakest, and this is nonpolar only. Strongest is hydrogen, and that has to be one of these three. And this one is the rest of polar. If it's polar, but it's not this, then it's dipole-dipole. This is an important thing. You'll have to do these starting tomorrow on your lab and starting today on your packets. Okay, so that's an important thing to look at. Note that every one of these bonds, every covalent intermolecular attraction is weaker, a lot weaker than that positive-negative electrostatic attraction for ionic substances. These are not, by any means, all solids. In fact, water is a liquid, and we'll find out soon it exhibits hydrogen bonding. So the strongest bonding, water, only gets to be a liquid at room temperature. Not even close to as strong as ionic. When hydrogen is covalently bonded to one of our FONs, and it's weakly bonded to an unshared electron, or unshared electron pair of a highly electronegative additive, the hydrogen gets really, really, really electron deficient. I'm going to draw a picture of this. Hydrogen has one proton in the most abundant isotope, and it's got one electron. Do you all agree with that? One electron, and it's 1s sublevel. What's the only element that can covalently bond when it's isoelectric with helium? There's only one element that can that will be isometric with helium. What is it? Isoelectronic, I should say. Hydrogen is the only one that'll be isoelectronic with helium. So if I put if I combine hydrogen with fluorine, fluorine has 1, 2, 3, 4, 5, 6, 7 electrons, and that shared pair of electrons will be right here. Do you agree? Now, fluorine is much more electronegative than hydrogen, so it's going to pull this pair of electrons with much greater vigor than the hydrogen. And when it pulls that, hydrogen's proton is going to basically be exposed because that electron is no longer orbiting the whole thing. It's spending its time over there. So what's exposed right here? A proton, which is positively charged. So the positive part of this, since this is hydrogen bonding, is very electropositive, very electron deficient. Because not only did this electron get pulled this way, after it got pulled this way, I've got an exposed proton right here. It's the only element that does that. Let's take a look at a similar diagram that we could write for chlorine, which has 7 electrons in its valence shell, and fluorine, which also has 7 electrons in its valence shell, and 2 here. So here's my shared pair of electrons. Fluorine, this red one, this is fluorine, can exert a stronger attraction for that shared pair than chlorine. What do you see that means that's true? Why does fluorine pull harder? Less shielding. You're correct. This is delta minus. And this one is delta plus. But if this electron pair is pulled closer over here, all it means is that these electrons are still going to be out here. They're just, I'm going to have a greater, if I could do a different color here and do an electron distribution, my electron cloud might look like this, sort of because I'm going to be a greater attraction over on this side. There's still going to be electrons over here. And since I have electrons over here, the exposed protons still have 1, 2, 3 shields between the rest of the molecules out there and this nucleus. Unlike hydrogen, which that's gone now, they're just right over here. This is going to be more like this. There's not much of anything out here. Does that make sense? So there's not much of anything there, which means that exposed proton is seriously positive. That's why hydrogen gets its own special kind of bonding. Here's a picture of hydrogen bonding. And you see what's going on there? Delta minus, delta plus, delta plus. There's this. And then the next slide is just like more. There's no mistakes there. But I think you get the general idea. So when I'm looking at these, they don't line up like this. They line up with this minus part and a plus part. And then over here, I'd have one of these. Then over there, I'd have one of these. And over here, I'd have one of these. And that's how they orient. If you've ever done that experiment where you see how many drops you can put on a penny, drops of water, the reason you can put so many drops of water on a penny is because of hydrogen bonding. It's what causes surface tension. Who's ever filled a glass up so full that it's like overflowing? Okay, you can't do that with gasoline. It's just flat because gasoline is nonpolar. So it's got London dispersion forces. Okay, the last thing, and we might talk more about this another day, but I don't think we'll need to. Network solids are when we have just a long, repetitive substance that's got a covalent bond to a covalent bond to a covalent bond. You have to know two. Diamonds, which are C, so it's C to a 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 C. Are you getting that? And the other one is silicon carbide, which is silicon carbide, silicon carbide, silicon carbide. And look at how interesting this is. Silicon and carbide. So C's can network solid. They can form a network solid. And Si and C can form a network solid. And they're both in group 4As. And we'll talk more about that in a few minutes. There they are. Diamonds, and I don't have one. Okay. Next, we're going to talk a little bit about this pink sheet and how you can use it. Look with me on the front side, please. This side. If you have a diatomic molecule, 2 atoms, what is the only possible shape? What is the shape that connects 2 points in space? A line, so it would be linear. Bond angle is 180, and they can be polar or non-polar. Do you agree with that? Flip this over and see if I have some diatomics on both the polar and the non-polar side. Do I? Pretty easy. So you can look at this to help you determine if something's polar or non-polar. Back to the front. For my triatomics, I've got a linear And we looked at that when we were looking at carbon dioxide. Do you remember that? Or my triatomics can be bent. And we looked at that when we were looking at water. The bent forms, I'm going to put these together and have you look at them. Here's a tetrahedron, a regular tetrahedron. And we'll talk more about this in a minute or two, or 5. This is a regular tetrahedron, and it's got 4 bonding sites. Do you agree? 1, 2, 3, 4. Look on your sheet. What is the shape that has 4 bonding sites and 4 bonding pairs? 4 and 4 in columns 1 and 3. Tetrahedron, 109.5. That's this. Now, if I lose this one, right in this spot right here, I could have a pair of electrons, like water does. And then I lose this one, I could have another pair of electrons. So I'd have 2 unshared pair of electrons right here, just like water does, making its shape bent. So this bent shape is 2 of the 4 vertices of a tetrahedron are electron pairs, unshared electron pairs, and the other 2 vertices have a hydrogen attached. So this is like the 4 vertices of a tetrahedron, but 2 of them are only electron pairs. There's trigonal, planar, and what element did we learn about last week that has 3 bonding sites? We did one on the front side of your packet. Which one only had 3 bonding sites? Do you remember which element? It was boron. Nitrogen sort of had 3 bonding sites, but it also has an unshared pair of electrons. So it has an octet. Boron was an exception to the octet rule. So boron can form a trigonal planar. And look at this line right here. What is one of my examples? BCl3. And there's no unshared pair of electrons. And a pyramidal, the trigonal pyramidal, would be like ammonia, NH3, and PCl3. There's a couple others that we'll talk super briefly about. Look at this group number 5. There's phosphorus, and 6. And there's sulfur. On the bottom 2 lines, phosphorus can have 5 bonding pairs. And if it does, what shape will it make? Second to the bottom. Yep, trigonal bipyramidal or trigonal bipyramidal. And sulfur can have 6 bonding pairs. And if it does, what will its shape be? Octahedral. You don't need to know anything else about those. The ones you need to know are on this side. And folks, until further notice, you can use this to help you decide if something's polar or nonpolar and what shape it is. Is that clear? This is a fabulous reference for using for that. And then when we're building, we'll do those. Okay. Next, we are going to watch a little video that you can find the link for on Moodle.